Okay, now we'll continue on costs and technology, moving a little bit beyond the textbook, okay, and more into some more recent research. And here we will try to connect costs and technology to market power in a very nice, theoretically consistent way. All right, but first, this is something that I'm sure you guys talked about before. If not, please tell me in class. Cobb Douglas example of the cost function. So go over the Cobb Douglas cost mean in the book and derive the total cost function. Here you have the minimum. So, for example, if you have two inputs, so you minimize this, which is your total cost, right? Because W is the input, the wage of labor, wage cost of labor per unit of labor, and then L is the total amount of labor. R is the per unit rental rate for capital, and K is the amount of capital. So this is like a total cost. To produce Q, some level Q, where you're using K and L as your inputs. And alpha and your beta are your coefficients to this Cobb-Douglas production function. Of course, typically there is an A here at the start usually, and that's like the technological progress term that sorts of lifts Q in addition to K and L. Now, take the FOC, first order condition, with respect to one of the inputs, say L, and it's this. So the left hand side is just if you increase L, then you increase your wages by you increase your total cost by the wage, okay, and it's equal to lambda. Lambda here is the Lagrangian multiplier of your constraint, if you remember that, and beta k alpha over 1 raised to 1 minus beta. This is simply the derivative of your production function. So this just says that, you know, if you increase L, your total cost goes up by W, but then you'll hit the constraint because you'll increase your output Q by this much. This is the marginal product of labor, and you multiply that by the shadow cost. So if, for example, if you are constrained by your constraint, then lambda will be greater than, will be greater than what else? Okay, here lambda also represents marginal cost because it's the value of slack in the production function constraint. Right, so it's the value in terms of total cost when Q, the target output, is less than what's able to be produced by your Q, by your production function here. So again, remember the left hand side is some target, and then the right hand side, which is also equal to Q, is in fact your production function given whatever K and L you've hired. So if there's a difference between the target and the production function, then lambda is sort of the cost of increasing your output by 1 unit, okay, by hiring both K and L. So that's called marginal cost, right? Because the cost of producing 1 unit is equal to is essentially is the same thing as marginal cost. Okay. So we'll go to the textbook right now just to check it out. It's this on this page 101. This is exactly what we wrote. We minimize cost subject to this. Okay, and then you've got a derivation here, which I invite you guys to check out. There are many ways to do this, but in the end, you will get to this. And then if you log the cost function, then it will become additive, like this. Okay. In fact, that's what we'll do. We'll take the logs of this cost function, and it's basically this thing right here, okay, where you've got this constant term, you've got the rental rate of capital, you've got the wage rate, and then you've got output here. Now you can take the derivatives d log c over d log q. That's equal to 1 over alpha plus beta. Okay. So we probably discussed this before, but I will talk about it again now. D log C over D log Q is essentially the elasticity of total costs with respect to changes in quantity. So this is interpretable as if you increase your quantity by 1%, by how much does your cost or total cost go up? And based on this, the answer is 1 over alpha plus beta. Okay. So, that's the next slide. So economies of scale is the situation is when output rises, cost rises, but by less than output. Okay, so this is also called increasing returns to scale. Okay, so if you go back here, if alpha plus beta is greater than 1, this whole thing will be less than 1, and therefore a 1% increase in Q will be met by a less than 1% increase in C. So increasing returns to scale is associated with alpha plus beta greater than 1. You can also see that here, and hopefully you guys talked about this in class before, in your micro class. In this case, if all inputs rise by lambda, then this is just you multiply each k and l by the same lambda. Then that means you can extract the lambda, and the lambda will be of the power alpha plus beta. If there are increasing returns to scale, alpha plus beta is greater than 1, and q with each capital and labor input raised by lambda is in fact greater than the old k and l, but output increased by scaled up by lambda. So this means it's better, you will produce more output if you scale up the inputs by lambda than if you just have if the old production function and scale up the output produced by that by lambda. So that's called increasing returns to scale. It's better to increase all of the inputs by lambda than have the old inputs and then just multiply it lambda times. So that means that output is reacting strongly to increases in your inputs. Okay. Constant returns to scale, of course, is when it doesn't matter. If you increase all inputs by lambda, it's as if you just multiply your output by lambda. Okay. So constant returns to scale, the interpretation there is, for example, if you had one, here's an example, one farm, for example, and if you increased your inputs, all of the inputs of your farm by lambda, okay, then it's as if you had lambda farms. Okay, it's the same thing as if you had lambda farms. So instead of lambda, let's use 2 times, or if you double it. If you double your inputs by k and l, then that means your output under constant returns to scale is just double. Whereas under increasing returns to scale, if you double your inputs, your output is more than double. So if it's constant returns to scale, it doesn't matter if you double your inputs or double the farms. It's the same thing. But it's very different if there are increasing returns to scale. So yes, there are diseconomies of scale and decreasing returns to scale, which is exactly the opposite if alpha plus beta is less than 1. And if it's less than 1, that means this thing is less than lambda, multiplying the output by lambda. Or in the total cost case, let's go back to the total cost case. If this is in fact less than 1, then that means a 1% increase in Q will increase your costs by more than 1. So from a production side, you would much rather not increase your inputs. It would be better to just double the amount of farms. So in that case. Okay, so hopefully everyone knows the difference between, or can link this total cost function or this production function to the idea of returns to scale, right? Which we discussed earlier as the relationship between average cost and marginal cost. These are all the same concepts, but here we're using a slightly more mathematical formulation. Alright, so let's go back to cost min. This time we discuss the production function method to uncover market power. Okay. You start again with the production function Q, which has inputs. They have two inputs, K and L. And we assume initially that we have constant returns to scale. Okay. So you minimize your cost subject to, again, this target Q is equal to this production function. And you get your FOC, which is similar to the other one, except now here, this is the marginal product of labor in general terms. And lambda is still the marginal cost. Now suppose there's a multiplicative markup. So mu is now equal to price over marginal cost. Okay. So now it's a multiplicative instead of the learner, which is P minus MC over P. This is sort of a multiplicative version. If you take the logs of the markup, then it can become the old learner markup. Anyway, we will focus on the multiplicative markup here, and then you can rewrite the FOC here as the following. W mu equals price times the marginal product of labor. And as you can see here, if mu is equal to 1, then price equals marginal cost, and that just brings you back to here, right? In that case, yeah, so it's the same thing. If mu is greater than 1 under market power, because price is greater than marginal cost, then W times something that's greater than 1 instead of 1, something that's greater than equals price times the marginal product of labor. So let's further derive or work with this expression. You can arrive at this expression. Mu, you focus, you isolate mu on the one side, and then you take things, you bring the other things on the other side. You've got PQ over WL times partial F partial L divided by Q over L. Okay. So first, this thing here is the inverse of the share in labor costs. Okay. And this one, epsilon LQ, this one, is the elasticity of output with respect to labor. Okay, so this one and this one, these are the two things, two components of the right-hand side. This left-hand side is 1 over 1 minus alpha, and this one here on the right-hand side is epsilon L epsilon Q with respect to L. Okay. You can do the same for the other inputs and all the other inputs really. So mu equals the elasticity of output with respect to capital divided by the share in capital. In other approaches, you can combine the inputs as changes in inputs K and L leading to changes in output Q, which is the production form. Okay. So that means you don't have to do it separately, you can do it jointly. So taking logs of our production function and taking total derivatives, we get the following. D log Q is equal to the elasticity of output with respect to capital times D log K plus elasticity of output with respect to labor times D log labor plus theta. Okay. So remember here that D log X is just dx over x, and that's how you're able to get this essentially. And theta is your technological progress term, generally speaking. So F will be affected by this technological progress term, which is now explicitly part of our expression. So let's interpret this. So this just says that the percent change in output, remember d log x is dx over x, so that's the percent change in Q, is just equal to the percent change in input K times the elasticity of output with respect to K, and plus the percent change in L times the elasticity of output with respect to L plus theta, which is the percent change in theta here, which is the change in technological progress. Now we can substitute the markup, because recall that here you've got the markup is a function of the elasticity of output and the share. So you substitute for the markup, you get this expression here. So now you can estimate mu using estimation techniques. You can estimate this using a regression. So the textbook shows how Hall's 1998 results for the US. And the US was Hall was able to measure mu, the markup, which is this multiplicative difference between the ratio between price and marginal cost for the United States. So I'm happy to say that I'm sort of continuing using this technique for the Philippines, and hopefully when it becomes a working paper, I can share it with everyone. All right, so now I'd like to, so armed with what we know, we can sort of read one of the papers, two of the papers really, mm, for for this class that I wanted you to read and write an essay about, a report about. So in the Global Market Power paper by DLE, okay, the Loker and Eckhout, they use the cost of goods sold and get the elasticity of output with respect to this measure and aggregate to the country level. They use the elasticity of output for the US for the different industries. Okay. But they have different countries, so they have a common elasticity of output. But they have measures for cost of goods sold and total revenue for which one? For all for many different countries across the world, including the Philippines. Now let's discuss some of the topics in the paper. So reallocation. So recall that they calculate markups at the firm level. Then they use sales weights. They use US elasticities of output that vary over time at a 2-digit NAICS level. So that with that, they can use this, essentially this one here, right? This equation here, which I can show you. Let's go back to the start of this one. This is a DLE paper. And I'll show you essentially what they're doing, which is this one. The elasticity here of output is alpha under their setup. Okay, and then this is the share, okay, or the reverse share, PQ over PV, and this is the markup here. These ones vary at the country, industry, and time level, and this one varies at the industry and time level, but not the country. So the markups can vary over countries and industries and time. Okay. So they're able to do that, and they use sales weights to aggregate up. So they have sales weights per industry, and then they calculate it at the country level and later at the regional level. So they ask, what is the role of reallocation to high markup firms of the rise in sales weighted markups? So first, they see in their results that, and this is their big finding, globally, markups are rising over time, and they want to know how this is allocated, right? Is it within the role of reallocation to high markup firms of the rise in the sales weighted markups? So is it true that markups are rising? Okay, or is it true that, or alternatively, is it true that sales are being redistributed to high markup firms? So what's the situation? Is it a composition effect, or is it just because, or is it in fact because markups are rising for everybody? So in figure 4a, they plot the distribution of percentiles, and it's clear that movement is driven by the high percentile firms. Okay. So the high markup firms are getting higher. The changes in markups was decomposed to changes of within firm markups and all the other forces of reallocation. Entry, exit, changes in the shares between high and low, and changes in both markups and the shares, the sales shares. So see Asia and the role of reallocation versus within firm growth. Okay. So please look at that paper and check out the results for Asia specifically. Next, and the world. Okay, so because we're in Asia and we're interested in Asia, we're interested in the world and Asia's place relative to say the developing countries or the world in general. Okay, and in class maybe I'll ask you guys to point that out to where that is. Okay, profits. They also study profits, which is the same as what we study, right? Which is this guy, right? Revenue minus costs, minus fixed costs. Then they call this the actual profit rate. This needs data on all the variables, W, L, R, K, F. And then they assume R is the same around the world. And they use profits over PQ as the profit rate. There is also an implied profit rate based on the profit function. We derive the relationship between markups, profits, and scale economies. Okay. So this is an important relationship here. Okay, so we'll try to linger here a bit. So mu, okay, the markup is just equal to price over marginal cost. And here we multiply both sides by AC. Both sides, numerator and denominator. And then you rearrange your AC, you move it to the left, and suddenly the left hand side becomes P over AC, and the right side becomes AC over MC. Now AC over MC should be familiar, and that's the measure of scale elasticity that we discovered before. P over AC, this is a measure of profit, because whenever there's a gap between price and average cost, there's profit. You can rewrite this by multiplying both sides by Q as total revenue over total cost. So this is an important relationship. It says that markups are high when profits are high and or scale elasticity is high. Okay. So that's important. So it's either markups are high because of market power, in which case it's reflected in profits, or profits could be small, but markups are still high because the scale elasticity is very high. All right, so that's an important result. Okay. So DLE, they measure a theory-based profit rate and assumes V is equal to 1. Okay. In the paper, they're able to calculate V, and in the Hall production function method, you're also able to actually estimate V at the same time as markups. Okay. So what is their relationship between the profit rate and the mu? So this is it. Okay, so this is the profit rate. Profit divided by total sales equals this thing, where mu tilde is their sales weighted markup. So as you can see, the higher the markup, right, the smaller this thing is, the larger this thing is. So the larger this has to be, assuming V is equal to 1. So there's a relationship, a nice relationship between the markup and the profit rate, assuming a constant V, and specifically if V is equal to 1. All right. So that brings us to the PCC paper. Okay. So there's lots to discuss when it comes to the results. There are some interesting trends in concentration indices, the things that we studied in the other video, and APCM, which is something that they call the adjusted price cost margin. Now the APCM that they calculate is really a profit rate, similar to what DLE, the Locher-Eckhout, was able to calculate, which is profit divided by sales, or value added. Volume of sales, we should say, volume of sales, which is essentially this guy here. And this comes from page 18. So essentially they measure a profit rate and call that APCM in the paper. Okay. So that should look familiar because it's the profit rate from the Locher et al. But you also know that the profit rate is not necessarily equivalent to the markups. This is due to markup profit scale economies relationship, right? So what is missing here is the returns to scale. So in the Medalla et al. Paper, they sort of skipped measuring returns to scale, and that could be something that can affect the relationship between the profit rate and markups. So note that in table 12, they document that APCMs are falling. If true, so first we note that APCMs are falling in the 2000s. That's very similar to the results in the Loker. So if you look at the Loker here, and let's hunt for Philippines. Okay. So the markup is basically a change of minus 17. The markup is 1.5 in 2016. And let's look for the graph for the Philippines. And it's this guy right here. It's increasing, and in the 2000s, something like maybe 2008, it falls down. Okay, maybe their last year here is about 2012, 2013 or something like that. Let's look at the PCC paper. They use a different data set. And in this data set, what they've got is basically a constant rate here, except for an increase in 2012. Okay, of 0.23, or rather a large increase in 2012. Or it depends on whether you exclude these capital intensive industries here. And if you do, then it's 0.12, 0.9, 0.10, 0.7, then suddenly a negative. This is also a capital intensive industry here. So it's kind of sloping down or constant during 2006 to 2014. So 2006 is roughly here, and to 2014, so it is also similarly falling in this region here. So that's good. That using different methods, essentially, they find that a similar sort of trend, especially when including C27 and C30, the PSIC 2 industries. Those two PSIC 2 industries. If true, then maybe markups are falling. But also maybe that scale economies are rising, which is one of the things that DLE also discovers.